All right, let's keep going. In chapter 18, aromatic substitution reactions. So we are going to be talking about adding things to benzene, substituting the protons on benzene, right? Benzene C6H6 has 6 carbons and 6 hydrogens. Now we are going to be substituting those hydrogens, and we're going to be talking about how we can build up our benzene ring. Always want to start with some fun, right? There's benzene waving to ya. Stubborn benzene, no, 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 no. Santa benzene, ho, 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 ho. Alien looking benzene. Yeah, that's weird. Yeah, it's funny. Okay, let's keep going on, right? We know that benzene does not react the exact same as typical alkenes, all right? This is where electrophilic aromatic substitution comes into play. We are going to be learning different ways to react benzene. Yes, benzene can react, it just takes a little bit extra. What's the extra? Well, halogenation does not work, but halogenation with a catalyst such as iron or a extra piece of the puzzle, the substitution does occur, right? And so this is where electrophilic aromatic substitution came to be. Also called EAS for short, the aromatic proton is replaced by an electrophile, and the ring acts as a nucleophile. Okay, so that's really important to understand that the benzene ring in these reactions will be acting as a nucleophile. We will see these 6 reactions in this chapter. Bromine and chlorine are essentially the exact same, but all of the electrophilic aromatic substitutions are very similar. Notice how the aromaticity of the ring is preserved at the end of the day. So, bromination of the alkene from chapter 8, Br2 was functioning as the electrophile. Why? Because it was polarizable, right? A Lewis acid catalyst, though, is needed to make Br2 electrophilic enough for our benzene ring, right? So this was what we did before. Bonk, bonk, and yes, we had back bonding occur, right? But this essentially was the electrophile and the pi bond was the nucleophile. Now, why adding iron worked is because iron with Br2 will make FeBr3, and that is our Lewis acid catalyst that we need to activate the electrophile Br2, okay? So we will see that FeBr3 is going to be added to our reaction. What happens first is we need to prepare the more potent electrophile. We need to prepare that reactive electrophile. How we do that is from some Lewis acid and base chemistry. Now, we didn't do a lot of Lewis acid base chemistry before. If you remember, it was way back in chapter 3. However, what we're looking at is a nucleophile attacking an electrophile here. Br is going to attack the iron. Transition metals are great electron acceptors because they have the d orbitals. There's some extra bonding going on in them. And so what this does is it actually makes our really, really potent catalyst. You can use this guy, or you can go one step further and say, woo, there he is, Br plus 1. That is crazy, right? I'm going to go ahead and use this whole guy right here to go forward. The FeBr5 minus 1 or minus plus this guy, right? We're going to say, okay, what's going to happen? Well, carbon can pick up that outer bromine, the one that was the most electrophilic position, and kick off FeBr4 minus 1. Now, what that generates is a new carbon to bromine bond. All right, I'm going to highlight it. New carbon to bromine bond. It also breaks aromaticity. The aromatic ring attacks the electrophile, and a sigma complex is the intermediate that is formed. It is a resonance stabilized higher energy intermediate. How is it resonance stabilized? I'm so glad you asked. The extra p orbitals are there to resonance stabilize this sigma complex. Now, the Br on the other, on the iron, the leftover bromine on the iron is actually going to do an elimination reaction to restore aromaticity. The second step of this reaction, if you consider the nuke attack as the first step, right, add the bromine, then we have to eliminate the hydrogen to complete the substitution. That is the exothermic step because it is reestablishing aromaticity for us, all right, and completing that substitution. From that, we get HBr, and FeBr3 is reformed, right? It's a catalyst. Skipped one. Addition reactions to the aromatic ring would be endergonic. So we only do substitution reactions, right? We're not going to add two halogens. Don't do an addition reaction. That would not be fun. We are going to see that the first step, adding the bromine, makes the sigma complex, the higher energy non-aromatic intermediate. And then doing the substitution by removing the proton will reestablish aromaticity. And that is what is exergonic. All right, with halogenation, we can also use aluminum, right? Aluminum tribromide is also okay to be a Lewis acid. It does the exact same thing as iron did. So FeBr3 or AlBr3, totally fine. Chlorine does the same thing, right? So Cl2 with aluminum trichloride or iron trichloride is A-okay as well, right? They do the exact same mechanism. Using F2 or I2 doesn't really work well. Fluorination, like always, is just way too violent to be practical. And iodine is really, 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 really slow. Back in my undergrad, I did try and develop I was part of the synthesis of a anti-cancer drug that we were trying to fluorinate, right? So we started with bromination, and then we chlorinated it, and then we substituted with fluorine, right, to see if the reactivity would be better. It was, but bromination is slow enough, y'all. Don't even think about iodination. That's way too slow. Iodine, not good. In fact, all electrophilic aromatic substitution mechanisms do the exact same two steps. We'll see a pi bond react, attack an electrophile. The sigma complex is all happy hunky-dory, stabilizing our high energy intermediate. And then the base, whatever, comes back and does a proton transfer to complete the substitution reaction. So we get an H being substituted by a common electrophile. All right. Next one, sulfonation. Sulfonation occurs by using SO3 as the electrophile and H2SO4 as the acid catalyst. Not a Lewis acid catalyst, now it is a actual proton, right? Bronsted-Lowry acid catalyst. Fuming H2SO4 is what contains SO3 gas. So you can see one of two things over the reaction arrow, SO3, H2SO4, or you can see fuming H2SO4. That means the exact same thing. And what we get is sulfonation to occur. We add SO3H to the actual molecule. Now, SO3 is a really potent electrophile. The sulfur atom itself has a significant partial positive charge due to inefficient overlap with the pi bond. So the SO bond itself has a significant single bond character already. And so what we see is our pi bond will react, boop, add on the sulfur, and kick up a pi bond onto one of those oxygens. We still have the sigma complex, right? Still having that beautiful resonance occur. And then we're going to use water as the idea of the base. We don't have hydroxide because we're in water, we're in H2SO4, and that would make H3O plus, and we can see that last little proton transfer is because we need to protonate the SO3 that was added, right? SO3H, so that we can take away that negative charge and make it neutral with the extra workup, okay? Sulfonation is a sensitive reagent but to concentration, so it is a reversible process. So if you can use concentrated fuming H2SO4 and actually make the SO3H on the benzene. If you add it to dilute H2SO4, you can actually reverse the process. This is going to be helpful when we talk about it a little bit later on in the chapter for synthesis techniques. All right, so nitration, again, same idea. HNO3 is going to be the source of the electrophile. H2SO4 is going to be used as the acid catalyst. You can think about H3O+, just like we used before. But it is believed that the nitronium ion, NO2 plus 1, is the active electrophile. Let's talk about how that is made, okay? So we have NO3 over here, just in case you didn't know what HNO3 looked like. There it is, HNO3. I know we don't often draw these Lewis structures when we use the acids in the lab, but there it is. What happens is the oxygen of the hydroxide on HNO3 is actually the most basic molecule. And the reason for that is the other oxygens are stuck in resonance. What that creates is a water-leaving group. And so the other oxygen will create an oxygen-nitrogen double bond and kick out water. There is our active electrophile. NO2 plus 1. The nitronium ion is highly electrophilic, so we can take it straight into our reaction with benzene. Benzene will attack the nitrogen and kick up an oxygen lone pair. That again creates a sigma complex, lots of fun resonance, so much rejoicing, and then water, right, which was produced in the preparation, is going to do the deprotonation, the proton transfer, okay, to reestablish aromaticity. Again, nuke attack the electrophile with benzene, sigma complex, joy, and then proton transfer that to finish. The nitro group is actually really interesting because that NO2 group, I'm going to draw it out here just so that we can see what it would look like. It has an oxygen with a negative charge and a nitrogen with a positive charge. Overall net neutral, right? But it is a reactive substituent. It can be reduced to form an amine using iron or zinc with HCl in an acid solution, and then NaOH is just there to make sure that we are neutralizing that nitrogen, because that nitrogen in an acid would form a protonated amine. So the NaOH is just as a little workup to make sure that we can have a neutral final product. Now, combining then all of these reactions, you can install the amino group onto a benzene ring, right? So we will be able to see lots of different uses for the amine at the end of the day, but you can start with nitration and then do reduction in the final two steps. Last two electrophilic aromatic substitution reactions involve adding carbon groups. Alkylation occurs by using an alkyl halide as the electrophile and using a Lewis acid. AlCl3 is typical. Now again, same type of catalyst function as what we saw before. Chlorine attacks the aluminum, and then what actually happens, if possible, secondaries or tertiaries, a carbocation will form. Secondary or tertiary carbocations are more than happy to exist, okay? And there is our electrophile. That electrophile can then undergo the electrophilic aromatic substitution that we have seen now 3 other times. Let's go through it anyway, just to be fun. Benzene attacks the carbocation, right? Beautiful sigma complex, lots of resonance. And then again, the Cl that added on to AlCl3, the AlCl4 minus 1, is what comes back and reestablishes aromaticity, okay? simple primary alkyl halides can be used. They are very effective. The only thing is that the primary carbocation cannot form. And so you would make that electrophilic agent just as a complex, looking at keeping the chlorine attached to the carbon. So again, the full thing is there. One big problem with this, simple things like ethyl groups can be used, but most alkyl halides that are primary are still susceptible to rearrangements, intramolecular rearrangements. So something like this, we could see that chlorine adds to the aluminum, but then we do that intrahydride shift in order to kick out the leaving group. And so that's where we would have a problem, and we actually see a big amount of products undergoing these rearrangements. So what's best is that you actually would try to use secondary or tertiary alkyl halides, or an alkyl halide, if it has to be primary, it's small ethyl groups so that there's no hydride shift that occurs. Also be aware with the alkyl halide you choose, rearrangements are always possible, hydride shifts and methyl shifts. Some other problems, just in case that didn't convince you. The halide leaving group must be attached to a sp3 carbon. Vinyl chlorides and benzyl chlorides do not work. These are sp2 hybridized. Nope, not going to work. Must be an sp3 carbon. Also, big old problem is that polyalkylation often results. You often get the para disubstituted product. Now, most of our examples will say, hey, assume that polyalkylation doesn't occur, but we're going to try to avoid Friedel-Crafts alkylation at all costs. And I'll show you a way to avoid it. But polyalkylation does truly occur in real life. Another thing is that some substituted aromatic rings, such as nitrobenzene, is too deactivated. So benzene needs to be a nucleophile, and nitro groups suck the nucleophilicity out of benzene. And so nitro groups do not react in Friedel-Crafts alkylation. All right, they just don't like it. They're not going to do it. So if alkylation doesn't kick you up a notch, acylation should work. Acylation is the new form of a carbon-carbon bond. Acylation requires an acyl chloride to react instead of an alkyl chloride. Notice here the acyl chloride group. That acyl chloride we will dive into more. It is a derivative of a carboxylic acid, and it has its own reactivity. But here with benzene, what it does is it adds that ketone group to the benzene ring. Same catalyst, AlCl3. So let's dive through that just to, again, see the similarities in the mechanism. Chlorine will add to the aluminum. And then the acylium ion is produced. The reason why the acylium ion is A-OK to produce is it is resonance stabilized. Let's draw the resonance there real quick. Bonk. Resonance stabilized. Now, typically the carbon will hold the negative charge, or hold the positive charge, better than an oxygen. However, it is still resonance stabilized. Let's go ahead and take that acylium ion into reaction. Attack the carbon, kick up the lone pair. Why that acylium ion with the oxygen as holding the positive charge is still probably a good thing to have, is because the other form has carbon with a lack of an octet, and nobody likes the lack of an octet. Sigma complex, beautiful. And again, the same old reestablishing of aromaticity. Some alkyl groups cannot be attached to the ring by Friedel-Crafts alkylation. because of these rearrangements. So that's where acylation followed by a reduction of the ketone group is a great alternative. So we would acylate first and then reduce. The reduction would be zinc mercury amalgam. That is an alloy. It's a combination of two metals, zinc and mercury, with HCl and heat. And all that does is it takes that beautiful old ketone that we put in the acylation and it reduces it to two hydrogens. How freaking cool. Unlike polyacylation, we do not see that, right? So alkylation can polyalkylate. We usually don't see polyacylation occur. The reason for that is because of the different style of group that we attached on, right? Not an alkyl group, we attached on an acyl group. It's a carbon with an electron deficient center because of the polarity here, right? Delta plus, delta minus. Nice. Two issues do arise though with adding a group to the ring. This is for any of our reactions that we just learned. We either add an activating group or a deactivating group, okay? So now the biggest thing that we have to consider is what happens when we have more substituents. What happens when we want to take a substituted benzene, something with one substituent already, and put on a second thing. So consider nitration of toluene here. We want to be able to say, okay, we know we're going to add the nitro group, right? This is what that is. We're adding NO2, but where are we going to do it? What does the CH3 that's already on benzene do to the rate of nitration? All right, so toluene actually reacts much faster than benzene, and it's because the CH3 group is an electron donating group. Carbons love to push electron density in towards other things because carbon is electropositive. And so carbon pushing in its electron density to the ring makes the benzene ring a better nucleophile. So with that, then we have to consider now, where do we put the nitro group? Cool, we can react faster now that we have this electron donating group, but where are we going to put it? What's the regioselectivity, right? What region of benzene are we going to put? Are we going to put it at the ortho, the meta, or the para position, all right? Ortho, meta, or para. Where are we going to put it? All three possible products could be installed, right? So let's talk about activating versus deactivating groups first. An activating group is one that donates electron density, typically. A deactivating group is one that withdraws electron density from the benzene ring. And if we're trying to make benzene a nucleophile, an activating group typically increases reactivity because pushing electron density into the ring makes it look like a better nucleophile. A withdrawing group decreases reactivity. Now, the things that we want to be able to say is what is going to push electron density into the ring, what's going to donate, and what's going to pull out, what's going to withdraw, okay? And that's where we're going to be talking about resonance versus delta pluses, okay? So typically carbon chains like alkyl groups push electron density into the benzene ring. They are what we call weak donators, weak activators, because there's no real electrons going in, but they do also have low need for those electrons. They like to push electron density elsewhere. Things like oxygens or nitrogens are what we call reactive or strong electron donors, because not only do they have a lot of electron density around them, they can push electron density into the ring via resonance, okay? So resonance allows us to actually activate this ring and see that the benzene is more nucleophilic, right? It has this extra lone pair now on it in the resonance structure, so there's delta minuses all around. A deactivating group is something that withdraws electron density, something that would pull the electron density away from the benzene ring. The most typical example is going to be our nitro group. And I'm going to, again, draw out the nitro group so that we can see nitrogen is the atom directly connected to benzene. It has an actual positive charge. That is pulling electron density out. We can even draw resonance where it would pull electron density out of the benzene ring. Right? Electron withdrawing. Also, carbonyl compounds. The electron density and the electron withdrawal from that carbon that is directly connected to our benzene ring. Again, that delta plus or actual plus directly connected to the benzene ring is going to be a withdrawing group. All right. We'll have one exception with the halogens, but we'll talk about that in the end when we actually start looking at the directing capabilities.